Today, we are going to unlock the secret language that powers almost all modern AI. And you know what? It's not code, it's probability. This is the playbook for how any artificial intelligence learns to navigate a messy, unpredictable world, and ultimately, how it makes smart decisions when it doesn't have all the answers. Well, they both have to operate with incomplete information, right? To make an intelligent choice, an AI can't just wait for absolute certainty. That would never happen. Instead, it has to make smart bets by constantly calculating the odds. And the mathematical tool it uses to do that, the very foundation of its reasoning, is probability. And this gets us right to the heart of the matter, the fundamental challenge that really separates today's AI from those old, rigid, rule-based programs of the past. It's this constant, relentless struggle against the unknown. It's all about dealing with uncertainty. So for an AI, uncertainty is basically the gap between what it can directly observe, the hard evidence from a sensor or a piece of data, and what it needs to reason about, those hidden variables, like what another driver is about to do. To bridge that critical gap, AI uses a framework called probabilistic reasoning to manage and constantly update its beliefs. Imagine this little robot here. It's hunting for a ghost. Now, its sensors are giving it clues, that's the observed evidence, but the ghost's actual location, that's the unobserved variable it really cares about. Since the robot can't see the ghost directly, it has to use the math of probability to build a sort of belief map of where the ghost is most likely to be hiding. Okay, so how does an AI even begin to tackle this? Well, before you can solve any mystery, you have to know what questions to ask in the first place. The very first step is to frame the problem with a formal, structured way of asking about the world. In the language of AI, a question is called a random variable. Yeah, it sounds a little technical, but honestly, it's just a placeholder for something we're uncertain about. And every single variable comes with a defined set of all its possible answers. We call that set its domain. For example, we could create a random variable r to ask, is it raining? And the domain, the only possible answers, are true, false, simple. Or t for temperature, with a domain of hot, cold. Or we could even have L for our ghost's location, where the domain is a whole list of possible grid coordinates. It's a really simple but powerful way of defining exactly what the AI is trying to figure out. Okay, having the right questions is a great start. But a question alone isn't enough, right? We need a way to weigh the likelihood of each potential answer. So, the next crucial piece of this puzzle is to actually quantify the AI's beliefs into numbers. For our temperature question, is it a 50-50 shot between hot or cold? And when it comes to the weather, how much more likely is sun than rain or fog? An AI can't just guess. It needs to assign a specific numerical weight, a probability, to every single possibility. And this is exactly how it's done. A table like this, which is called a probability distribution, acts as the AI's belief sheet. So for temperature, it believes there's a 0.5 or 50% chance of hot and a 50% chance of cold. For weather, it's assigning a 60% chance to sun, 10% to rain, and so on. Notice it's even assigned a 0% chance of a meteor strike. This is the moment belief becomes actual math. And there's one non-negotiable rule that keeps this whole system honest. All the probabilities for any given variable have to add up to exactly 1. This formula just means the chances of all possible outcomes must equal 100%. It's basically a logical sanity check. After all, the weather has to be something, right? This makes sure the AI's beliefs are always consistent. So, knowing individual probabilities is a great start. But the real world is messy and interconnected. The true power of probabilistic AI, the thing that makes it feel so intelligent, comes from its ability to connect these different variables and understand how they influence each other. See, our belief sheets tell us the chance of hot is 50% and the chance of sun is 60%. But what about the probability of a combination of events? What's the chance that it's hot and sunny at the same time? Our individual tables can't answer that question for us. For that, we need a joint distribution. Think of this as the AI's master cheat sheet. It gives us specific probability for every single possible combination of outcomes. So now we can just look it up. The probability of hot and sun is 40%, or cold and rain, that's 30%. This table connects all the dots. And this little robot judge is the perfect metaphor. Armed with its joint distribution table, the AI can now act like a judge, considering all the variables together to weigh the likelihood of any complex situation. It finally has a complete, unified model of its world. Okay, so we've built a complete model of the world. Now for the magic. This is the part that truly matters. What happens when the AI gets new information from the real world? How does it actually learn? Let's walk through a scenario. So we get a new, undeniable piece of evidence. A sensor confirms the temperature is cold. How should this fact change what we believe about the weather? Should we still think there's a 60% chance of sun? Almost certainly not. Our model has to adapt. And this right here is the core engine of learning in probabilistic AI. It's this elegant three-step recipe called the normalization trick. First, you select all the outcomes from your master table that are consistent with your new evidence. Second, you sum their probabilities. And third, you divide to rescale them into new, updated beliefs. Let's watch it happen. Okay, step 1 is select. Our new evidence is that the temperature is cold, so we go to our master cheat sheet and we just eliminate every single row that doesn't match this fact. Instantly, the AI's world of possibilities shrinks. Now it knows it can only be cold and sunny or cold and rainy. That's it. Step 2, sum. We add up the probabilities from our new, much smaller table. So 0.2 plus 0.3 equals a new total of 0.5. This number, we'll call it Z, represents the total probability of this new, smaller world we're now living in. But notice, our probabilities no longer add up to 1, so we need one final step to make them consistent again. And that's step 3, divide. We take each probability from our selected rows, and we divide it by our new total, Z, which was 0.5. So 0.2 divided by 0.5 becomes 0.4, and 0.3 divided by 0.5 becomes 0.6. And just like that, we have brand new, updated beliefs. Given that it's cold, the AI now believes there is a 60% chance of rain, which is a massive jump from its original belief of just 10%. It is literally learned from experience. This simple three-step process is so much more than just a neat math trick. It is the fundamental mechanism that allows an AI to learn from data. It's what makes AI adaptable, responsive, and, well, intelligent. It all comes down to this single, incredibly powerful idea. Every single time an AI observes a new piece of evidence, whether it's a pixel in an image, a word in a sentence, or a new stock price, it runs this exact update procedure. Its beliefs about the unobserved parts of the world are constantly shifting and sharpening. This is learning in its purest form. But this leaves us with a fascinating and really critical question. Our entire process assumes that the evidence we get is 100% reliable. What happens when it's not? What if a sensor is faulty or a data source is biased? If an AI is constantly reweaving its model of the world, how does it decide which threads of evidence to trust? And that is where things get really interesting.